Hello, and today we're going to do Texas ranges. Welcome to Haskell. So it's been interesting so far on the value level. On the value level, yeah. These all stuff that we did, and I guess if you don't really practice it, you forget it. The drop, the null, reverse take, all of these kind of imperative like um, operations. Yeah, they are like operations because they somehow change the object, the list, and if they don't succeed, if they fail, we just get an exception. And that's kind of, I guess that's not in the true spirit of functional programming or denotational design. To to quote Connell, this is an amazing talk, and you kind of get so inspired that you almost get, why am I doing this? Okay, yeah, that was not clear. But today we're going to do Texas ranges, and it's not actually about Texas. Yeah, this might be confusing. No, it's just about ranges. Ranges in the sense of, it's like when you have a linear kind of uh, row of things that you have, right? As in from 1 to 20, and that would be a kind of a range. That range can have a step though, like you could say, give me all even numbers. So we have like a range of even numbers. Or you could have a range, I guess you could have a range of infinite numbers. Like, okay, I don't have a console opened up yet. Why don't CD? So a range would be like 1 to 20. Yeah, let's see what he says. What if we want a list of all numbers between 1 and 20? Sure, we could just type them all out, but obviously that's not a solution for gentlemen who demand excellence from their programming languages. Okay, gentlemen. Instead, we'll use ranges. Ranges are a way of making lists that are arithmetic sequences of elements that can be enumerated. So making lists that are arithmetic sequences of elements that can be enumerated. Well, I guess if you could make a range of an infinite list of numbers, and you make would that include a range? Like, does range numbers can be enumerated 1, 2, 3, 4. Characters can also be enumerated. The alphabet is an enumeration of characters from A to Z. Names can't be enumerated. What comes after John? I don't know. This is an interesting thing with naming. So you can never guess the next name, right? Even if you have like billion names, we cannot project. Okay, you could project what would be the next name, but that's just based on, some kind of heuristics. But you do not know what is going to be the next name. You just don't. So that would not be a range. But I'm curious, just if in range of an infinite list, would that be a range? Let's ask ChatGPT. Maybe ChatGPT knows. So the alphabet is an enumeration of characters from A to Z. Ranges are a way of making lists that are that can be enumerated. Okay, let's just copy this. So this is the ChatGPT 4.0, the new one. I don't know how you read that, 4.0. Okay, this so says learn you a Haskell about Haskell ranges. in lists. Now I'm curious if a range is an infinite list, such as 1 and this. A range is a way to create lists that follow an arithmetic sequence. 1, 5 creates a list of 1, 2, 3, 4, 5. Haskell's lazy evaluation allows for the creation of infinite lists using ranges. Yes, 1 is indeed an infinite list. The notation generates an infinite list of all natural numbers. Because Haskell uses lazy evaluation, it won't generate all the numbers. Yes, we know that. I guess we do. Infinite lists. Yeah, because you can take out numbers from an infinite list, right? Because if I would write this, this would never compute. I would get an exception. Like, look at this. It's just going on and on. This is like the C matrix program, and it's kind of cool. I think it will get slower. Will it get slower? Wow, this is nice. Okay, let's stop. Stop. Please stop. What, 367,534, 367,533. Oh, it's counting. It was basically counting. Nice. But if we take 100 from a list, from an infinite list, so it will just take, you see, take 100 from an infinite list, and it just takes 100. Maybe it will work like take 100 from a list of 1 times, let's try this, 1 times 9. And this. Will this work? 9, 10, 11, 1 times 9. 9, 10, 11. Oh, interesting. Take 100 from 1 times 9. 2 times 9. Try this. Oh yeah, it did work. So I wrote the second step. 1 times 9, 2 times 9. So now it's taking 9. 1 times 9 is 9. 2 times 9 is 18. 3 times 9 is 27, and so on until 900. It can do stuff like that. Okay. To make a list, but yeah, the point was like you cannot enumerate a name. Like the next name, which it sounds very deep, like a deep black hole. Like, why is that true? To make a list containing all the numbers from 1 to 20, you just write 1 to 20. Okay, we get that. That is the equivalent of writing 1, 2, 3, 4, 5, 20. And there is no difference between writing one or the other, except that writing out long enumeration sequences manually is stupid. That's stupid. Stupid. Okay. Well, I don't know if it's stupid. Maybe it's a bit silly. 1 to 20, A to Z, K to Z. I guess you could make steps with A to Z also. Like, you could make like A, and then C. I guess now it would skip every second letter. Oh, what's going on? Oh, it did numbers. Why did it do numbers? But it's different. It has a slash. Maybe it was counting all the letters in circle. 1, 2, 8, 5, 6, 1. We probably have it repeated. 1, 2, 8, 3, 2, 3, 1, 2, 8, 5, 8, 3, 6, 2, 7, 1, 2, 7, 3, 3, 9, 1, 2, 6, 6, 1, 2, 5. No, it didn't. It was counting. Wait, let's try again. Let's take 100 from these. Oh, this is interesting. So A, C, E, G, I, K, M, O, Q, S. Yeah, so it skipped every second letter. But then it goes to delete, del, and all the characters. These are some kind of characters. Like, what are these numbers? ChatGPT could know this. Generating the first 100 elements of the list starting from A. ASCII values with the step 2 in their ASCII values. Whose ASCII values are 97, 99, 101, 103, and so on. Character sequence AC creates a sequence beyond printable ASCII. When the ASCII values exceed 127, it starts producing non-printable or extended ASCII characters, which is why you see characters like del, ASCII 127, and then extended ASCII characters during. Okay, that's the reason. So it was still doing the same thing. All right. Good. So ranges are cool because you can also specify a step. What if we want all even numbers between 1 and 20, or every third number between 1 and 20? 2, 4 steps to 20, all right. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 3, 6, and then 20, 3, 6, 9, 12, 15, 18. Yeah, this is fine. So I could make like, it's going to take, okay, I'm like 1, 1, and 5. Maybe I could do like 0 and 5. Let's start from 0 up to 20. You get 0, 5, 10, 15, 20. I think for me it looks kind of better. Why did he start with 1? Okay. Yeah, I think it's kind of, I don't know, it's more intuitive to start with 0. It's kind of more symmetrical. Like, let's say 3 and 20. 0, 3, 6, 9, 12, 15, 18. Yeah, because when you do this from 1, it's not, I think it's not that clear. 1, 3. Oh, wait. 20. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. Yeah, it's interesting, but this is, I guess this is more correct. Yeah, look at this. 0, 3. Yeah, you cannot get uneven numbers. Look, I did 0, 3, 6. 9, 12. All by 3. When I start counting with 1, I have a mosquito and I'm trying to like do like softly send him away. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. Yeah, it's interesting. So I guess I would have to write 0, 3, 5. Just a moment. All right, so I caught the mosquito and I let the mosquito out. Don't kill mosquito. All right. Yeah, I was the 0. I guess you could do like 0, 1, 3, and then 20. Would I get the same list? Parse error on input. Oh, it won't work. Interesting. So 0, 1, 20. Let's see this. 0, 1, 2, 3. Yeah. Why is it now 0, 1, 3, 20? No, it's not working with a step. But if I just do 1 and 3, 20. Yeah. Well, okay. It's simply a matter of separating the first two elements with a comma and then specifying what the upper limit is. While pretty smart, ranges with steps aren't as smart as some people expect them to be. You can't do 1, 2, 4, 8, 16, 100. 1, 2, 4, 8. Oh, that's like, what's it called? Quadratic progression. I don't know. So it's like 1 times 2, 1 squared. 1 squared 1. Like 1 squared is 1 and then 2. Okay, then 2 squared is 4. 4 squared is 16. No, this is not. This is double. 1 double, 2 double is 4. 4 double is 8. 8 double is 16. Yeah. Double 1 double is, yeah. And expect to get all the powers of 2. Firstly, because you can only specify one step, and secondly, because some sequences that aren't arithmetic are ambiguous if given only by a few of their first terms. To make a list with all the numbers from 20 to 1, you can't just do 20 to 1. I guess you could read this 2, the range, 20 to 1, because it says 20 to 1. I don't know what's the Haskell way to say this, like 20 up to 1, 20 to 1, not sure. Would be nice if you like teach someone. I mean, like, it's great that you use words, all kinds of words, but it would be nice to have like at a sidebar or something, like what's the proper way? Proper, that's not the right proper word, but like what's the common way or the common terminology or the mathematical way to say this? Maybe it's helpful. I don't know. Sometimes I find it helpful to compare yeah, words like that. To make a list with all the numbers from 20 to 1, you can't just do 21, you have to do 2019 1. Okay. Watch out when using floating point numbers in ranges because they are not completely precise by definition. Their use in ranges can yield some pretty funky results. 0.1, 0.31, 0.0570. Okay, yeah, floating point numbers. My advice is not to use them in list ranges. So I guess the proper term would be list ranges rather than Texas ranges. This is the first time he says that. List ranges. You can also use ranges to make infinite lists by just not specifying an upper limit. Later we'll go into more detail on infinite lists. For now, let's examine how you would get the first 24 multiples of 13. Sure, you could do 13, 26, 24 times 13, but there's a better way. Take 24. Take 24, 13, 26. Yeah, this is again something, it's still okay, it's still operational and on the, value level, but like you see this, like you're trying to build a list and this one has a function that takes 24 elements of a list that is an infinite list basically, right? And it takes the 24 elements with this that has this kind of a step between each of them. So that's better than making a list and then doing 24 times 13. 24 times 13. Oh, like 1326 up to 24 times 13. Yeah, let's examine how we get to first 24 multiples of 13. That's interesting. So like first, let's do it with 2 and 4 up to 24 times 2. Two multiples. Yeah, I guess I should put 4. So we get 2, 4, 6, 8, 10. So these are the first 24 multiples of 2. And 2 times 24 is 48. So you get like, so instead of this, you take the first 24 multiples of 2. You just put 2, right? No, you have to put 3. Because it would just start from 2, yes. 2, 4, like this. And now it creates an infinite list. But because it's, you know, lazy, it will stop after we just take, like, give me just 24. 24 of those. And it gets us the same result. And this is kind of more functional in the sense that there is a list here, and there is a list that there is a list with a range, and there is a function that takes 24 of those elements. Because Haskell is lazy, it won't try to evaluate the infinite list immediately because it would never finish. It will wait to see what you want to get out of that infinite list. And here it sees you just want the first 24 elements, and it gladly obliges. A handful of functions that produce infinite lists. Moment. We're recording? Yeah. So a handful of functions that produce infinite lists. Cycle takes a list and cycles it into an infinite list. If you just try to display the result, it will go on forever, so you have to slice it off somewhere. So take 10, slice 1, 2, 3. Cycle 1, 2, 3. All right. That's like a clock thing, I guess you could say. Like take 5. Yeah, take 5 and cycle, because it's a function. We open up parentheses and then a list of 1 to 12. And take 5. 1, 2, 3, 4, 5. So I guess you could take 5, the last of, or in it. Yeah, if you just write last, take 5. Yeah, would this work? Time is a last composed with take. This work? No, not work. Wait. Time. What time is last? Last. I guess, or like a lambda. Last. Take X. Would this work? No, it will not work. Yeah, I'm trying to like, okay, so let's say we have a list. Let's do clock. Clock is a list 1 to 12, or let's do 24. Okay, so we have clock, right? It's a list. It's from 1 to 24. It should be from 0, right? Or not, because we have 24. 24 is the 0. Maybe we should do 1 to 23. 0 to 23, yeah. We could redefine it as 0 to 23. So now clock is 0 to 23. 0 is, what would be 0? Would 0 be noon? No, noon would be 12. So 0 would be midnight. Okay. So now if I say take 5 from clock, I get 4 o'clock. 0, 1, because I'm counting. Oh yeah, this is now confused. I want to say like take 5. So we have to take 6. Take 6 from clock is 5. I want to do the last take 6 from clock. So I get 5 o'clock. Take 6 from a clock. Yeah, I would have, it would be better actually to count from 1 to 24. Let's redefine it. 1 to 24. No, 24. So we have a clock, 1 to 24. And last. So now we have last, take 5 from clock, and we get 5 o'clock. Yeah, what am I trying to do, right? Like, what's the time? All right, this was, maybe this was, okay. Cycle, but anyway, cycle makes a list and it kind of cycles it, which is not true. If we take a list, did I take a cycle? I did not even do a cycle. Take 5 from a cycle. Oh, I made a list. You see, it's what a mistake. I made a list and I didn't even use the cycle. I should have used the cycle. Cycle 1, 2, 3, but it wouldn't work. I could do cycle clock. Oh, okay. Look, I could do take 5, but then it doesn't show it. Let's do more. Take 100 from a cycle of clock. Yes. So I do 1, 2, 3, 4 up to 24, and then again, so it cycles from 1 to 24 and then back 1 to 24, and it stopped at 4. So when I said take 100, and it creates an infinite clock list, but it stops at 100. All right. Repeat takes an element. I admit this is not the most fun part for me in learning Haskell, because yeah, I guess I miss abstractions. Repeat takes an element and produces an infinite list and just the element. It's like cycling a list with only one element. Repeat 5. So it won't work. I guess it won't work with repeat 1, 2. No. Yeah, we have to take 10. Repeat A. Will it work with like apple? Apple. Okay. Take 10. Repeat. Maybe like this. AB. Ah, okay, it works like that too. Take 10, repeat AB. It just repeats AB. Like here, repeat 5, repeats 5. An infinite list, I guess. It creates an infinite list. It's like repetition without an end. Although it's simpler to just use the replicate function if you want some number of the same element in a list. Replicate 3, 10 returns 10, 10, 10. Oh, replicate 3 tens. It creates a list. So this repeat 5, maybe you want like, oh, I see, take 10, repeat 5. Would be like replicate 10 5s, right? So you had take 10, repeat 5. So this gives us 10 5s. So it would be better to replicate 10 5s. That's it. Yeah, this is less typing and one function. I'm a list comprehension. Oh, list comprehensions. If you ever taken a course in mathematics, you probably run into set comprehensions. They're normally used for building more specific sets out of general sets. Okay, a basic comprehension for a set that contains the first 10 even natural numbers is S set is, and then this curly braces, 2 times X, and then this thingy here. X is an element of a set of natural numbers. That's one condition. I guess these are the conditions. And then comma, and then the second condition, that the X needs to be lower or equal than 10. So we have two conditions. X is an element of the set of natural numbers, which are numbers, I guess, from 0 or 1 up to, an infinite list, not negative numbers. So And the second condition is x is less than or equal than 10. So these are the two conditions, but now you want 2 times x, 2 times that number. So you want only the even numbers. Yeah, that's the way, that's the 2 times x. I guess that's the way how you would write that. The part before the pipe, oh, that's the pipe. This straight line, straight vertical line. The part before the pipe is called the output function. X is the variable, n is the input set, and x less or equal than 10 is the predicate. X is the variable. Okay, so these are the kind of, it looks like the two conditions, but it's described a bit differently. So the part before the pipe, so this is the output function, and x is the variable, and n is the input set. So x is an element of this set, also means x, okay, that's the input set. That's the what we are getting at to work with. And this is the predicate. So x has to be what? Okay, this is the input where it's coming from, and this is kind of like a filter of sorts. So not really filter. Actually, this would be better described as a filter, and this is a predicate. How would you describe a predicate? Yeah, up to a point. Also some kind of a filter. That means that the set contains the doubles of all natural numbers that satisfy the predicate. If we wanted to write that in Haskell, we could do something like take 10 and 2, 4. Yeah, but what if we didn't want doubles of the first 10 natural numbers, but some kind of a more complex function applied on them? We could use a list comprehension for that. So yeah, it's just basically he's doing more functionality. It's still kind of operational wise. List comprehensions are very similar to set comprehensions. Well, it's not. This is not operation wise. This is very clear. Okay, let's continue. List comprehensions are very, list comprehensions are very similar to set comprehensions. We'll stick to getting the first 10 even numbers for now. The list comprehension we could use is x times 2 and then x 1 to 10. Oh, I see. Yeah, we don't have to write x as an element of natural numbers. Because, oh wow. This is cool. This is almost like, yeah, sorry. I was reading something about dependent types. So it's like independent types, which is really cool, and I think I'll have to wait for a year until I get there. But dependent types are so cool because you can like describe the types with values on top of it. Like okay, you can say a type, my function will have a this kind of a type. But these are more like, they're not so clear, the descriptions. Like, okay, my function will have a type of a natural number, right? But with dependent types, you could even put this inside of a type declaration. So instead of just writing this, you see, you could add x is a type of a natural number. That means if somehow your function gets a, negative number or something, it will not be an exception. Like you would not have to program what would happen if you have an exception of sorts. Like if an exception comes, then write blah blah, like the empty head of a list. So this is cool how this popped out, because I was almost now sure that I will get to write x is an element of the set, but this, you would write like this in Agda, programming it. See, this is like, so greeting, hello. You see nat dependent types. Where is it? 0. successor. Yeah, it's like all of these things are now defined in types, as types. So that means you have proofs that the function will work or not. Yeah, anyway, this is I didn't even scratch it bit, but this was kind of interesting that this would be actually declared in a type. And here we are just kind of reading about it as in how it's written in math. So, okay, let's do a list. So it would be like x, okay, we want even numbers, x times 2, right? And then we use a pipe, wait, let's write it here. And then we use a pipe, and now we're gonna say what comes into my x. So the input function into x, and it's kind of nice, you can use this, you know, symbols, come 1 to 10, right? We have to close it because we opened the list here. So this whole thing is a list, right? And you get this. So, but we can use stuff like from before. Like I think we could use this cycle 1, 2, 3. We do this, and then like take 10. No, it won't work. All right. X times 2, as you see, I don't know Haskell. X times 2, x. Okay, well, this is clear. As you can see, we get the desired results. We do. Now let's add a condition. Oh, we don't have a condition or a predicate to that comprehension. Predicates, okay, predicates go after the binding parts and are separated from them by a comma. Let's say we want only the elements which doubled are greater than or equal to 12. So yes, we did say we want even numbers, and those even numbers are going to be from 1 to 10. No, this is not true. We don't want even numbers. Yes, we want we double them. No, this is not, I was saying it in the wrong way. So the input function will be from 1 to 10, and we're going to double it, x times 2, and x is from 1 to 10. So 1 times 2 is 2, 2 times 2 is 4, 3 times. So we are actually not getting the even numbers. We are doubling each member of this list, and we get this list. That's why it's also bigger, this list, than the 1 to 10. So here, let's say we want only the elements which doubled are greater than or equal to 12. So it was so wrong. Yeah, x times 2. We're going to do this. So x times 2 basically means we're going to do this with every x. So we're going to double it. Okay. And x is going to take what? It's going to take a list from 1 to 10. Okay, so now we have like before, so we're going to double each member of this list, but not so much. Wait, x times 2, we have to repeat the predicate, but only if x times 2. So give me that list, but only if, give me only those, yeah, give me only those x times 2's, give me only those doubles, I guess, that are greater than or equal than 12. So now it's going to do 12, 14, 16, 18, and 20. It's same as before. The same as before, right? But now, you see, we're given an extra predicate. You can even, I guess you could put them more, like, okay, greater than 12. And maybe x mod 3. X mod 4. How would that work? No. I'm horrible. Okay. Okay. Cool, it works. How about if you wanted all numbers from 50 to 100 whose remainder, when divided with the number 7, is 3? Oh, that's the mod. Oh, that's how you write the mod. Okay. Whose remainder when divided with number 7 is 3. Easy. Yeah, I was always confused with mods and remainders. GACI, x Okay, x, we put a pipe, and x will take what? 50 to 100. All numbers from 50 to 100. All right, 50 to 100. I guess this is the beginning of like doing rules and then meta rules, because in higher order functions and more complicated abstractions, you'll have a function that has more properties, or like meta rules, like a rule that has a rule and that has a rule, or a rule that has rules. So like this function can do this and that, and this doing itself has some kind of a rule that it has to satisfy. That's gonna happen, you know, like with higher abstractions. So even though this is still at the value level, but these are like, this is something similar in the sense we have a rule, 50 to 100. So give me the x, and this x is going to be 50. So like even this would work like this. So it's 50 to 100, right? But now let's do more. Let's refine it, or like let's filter out what. But we want only those numbers. Okay, so now some kind of a meta rule. So this is a rule, 50 to 100. And now we're going to put another rule on top of it. So like to whose remainder. So the remainder of the numbers from 50 to 100, whose remainder when divided with the number 7 is 3. So this will, like, I wouldn't know how to do this, like 51. So it will be like whose remainder when divided with number 7 is 3. So like 52 divided by 7 is the remainder 3. I don't know. So you do x mod 7 is 3, is equal to 3. And then you get 52. And you can divide 52 with 7, and you don't get 3, right? You get 52, right? It's 52 divided by 7. Oh, I see. But yeah, it's like 21. I can see that. So 52 minus 21 is 31. Yeah, these things were always like 52 divided by 7 gives the remainder 3. Okay, 52 divided by 3 is 17. Yeah, I guess I remember. You need to check up on the mod thing. You need to check up. Whose remainder when divided with number 7 is 3. Easy. Whose remainder x mod 7 is 3. Mod 7 is. Let's ask this to ChatGPT. Explain in Haskell. To generate all numbers from 50 to 100, you can use list comprehensions. All right. List comprehensions provide a concise way. Here's how you can do it. Range 50 to 100. This creates a list of numbers from 50 to 100. Generator. Oh, this is the generator. He didn't use that word. X takes each value in the range from 50 to 100. So this is the generator. Okay, so this is the range. 50 to 100. Wait, check this out. Can I put this? So range, this is the range. This creates a list of numbers from 50 to 100. And this is the generator, x. All right, the generator function. The generator x takes each value in the range from 50 to 100. Okay, the condition. What's the condition? Okay, so we have a range, a generator, and a condition. This is clear. The condition filters the numbers in the list such that only those such that, yes, such that, that's the expression that's often used. The condition filters the numbers in the list such that only those numbers x for which the remainder when divided by 7 is 3 are included in the result. Yeah, this is worded in a bit different way. List comprehension. So this constructs the list of numbers that satisfy that given condition. When you evaluate the numbers expression, you will get the list of numbers from 50 to 100 whose remainder when divided by 7 is 3. Numbers, the output would be, and he puts it already in a variable. So that means like you can, yeah, it's nice. Like if you put this in a file, then you can use them. Like, you know, numbers, and you would get them out. It's not bad. Let's evaluate the expression to, yeah, because now we just put this stuff in GCI and it's all lost. And otherwise, you know, if you like, we do this and do numbers, and you know, you can have it, you can call it again. Numbers, the output will be 52. These are numbers to, but why is, okay, now I don't know. Why is when I divide 52 with 7, I get a number with more decimal points? I'm not clear where is the remainder. When you use div and mod functions, you're working with integer division and remainder operations, not floating point division. Oh, I was thinking too far. Integer division, this divides two integers and returns the quotient without the fractional part. Modulo returns the remainder after dividing two integers. This was always confusing. Oh my god. Div and mod. Let's clarify this 52 integer division. When you perform 52 div 7, you get 7. Because 52 divided by 7 is 7 with the remainder. So 52, I was doing the floating point. Div 7 is 7. Yeah, I was doing 50 div, no, I was doing this. And you get a floating number. Okay, I should have used div, I guess. Remainder. When you perform 52 mod 7, 52 mod 7, you get 3. Because 52 divided by 7 is 7 with a remainder of 3. Okay, 52 divided by 7. Okay, 52 divided by 7 is 7. 7 times 7 is 49, remainder 3. Clear. Quotient 52. Okay, 52 divided by 7, this will give 7. This is the quotient. Remainder 52 mod 7, this will give 3. Remainder. Oh, okay. Floating. It's nice how he puts it in variables. Floating point result is. So it's kind of like a definition. 52 divided by 7. This will give approximately 7.4. Calculation verification. Okay. He does. Kind of does. Okay, you'll get thumbs up. Okay. Success. Note that weeding out lists by predicates is also called filtering. Yes. We took a list of numbers and we filtered them by the predicate. Now for another example, let's say we want a comprehension that replaces each odd number greater than 10 with bang. And each odd number that's less than a 10 with boom. It sounds like the, what's that programming? I remember I used to read about it. Now it's not mentioned. FizzBuzz. Yes, the fizz buzz. Like generate the numbers from 1 to 100, and each uneven number is like fizz, and each even is buzz, and one more number is like, I don't know. Yeah. That was like the common programming assignment giving on an interview, which kind of sounds silly, but okay. Now for another, okay, let's say we want a comprehension that replaces each odd number greater than a 10. So these would be more predicates, right? We'd have an x, and then we have a list of numbers like a range. Then we have a generator that we input that into the x, right? So we have the x, and then we have the generator with the x, and then the predicates. Now, one of the predicates would be that to replace each odd number greater than 10 with a bang. That would be one predicate. And the second predicate would be each odd number less than 10 with a boom. And the third predicate, if a number isn't odd, we throw it out of the list. So I guess we'll have, I'm not looking at the definition that it's right in front of my eyes. I'm gonna just, I put it into words. So let's see, for convenience, we'll put that comprehension inside a function so we can easily reuse it. Boom bangs, boom bangs, boom bangs, x's is what? Okay, if, oh, he's using already if. Yeah, I thought he's gonna put this at the beginning. Let's just check. What would ChatGPT do immediately, and then we'll go back to it. All right. So he's doing if x is then doom, else boom. If a number isn't odd, we throw it out of the list. If a number isn't odd, so if he starts the other way around. If x is less than 10, okay, then boom. Else, okay, else bang. Really? Replaces each odd number greater than 10 with a bang. If x is greater than 10, if s, oh, he's again doing it. Oh, that replaces each odd number greater than 10 with a bang. And each odd number that's less than 10 with a boom. And then he says, and he starts with a boom. If x is less than 10, then boom. Else bang. If a number isn't odd, we throw it out of the list. So how do you put this? I thought you... And then the pipe. For convenience, we'll put that comprehension inside a function. The last... Ah, this is so unclear to me. Sorry. Let's see what... To create a Haskell function, else boom. Wow. Yeah, he started bang, then boom. You see this? Bang, boom. To create a Haskell function that processes a list according to the given rule, we will define a function that takes a list of integers and uses list comprehensions to replace each odd number greater than 10 with a bang, and each odd number that's less than 10 with a boom. If a number is not odd, it will be excluded from the list. So if a number is not odd, just don't put it in the list. A bang boom is a type. Oh, he writes the types. That's nice. A bang boom is a type from an int to a string. Yes, because we are the function takes as an argument of a type int, which is a list of numbers, right? And it outputs a string. You see, it outputs strings. So it's a function from int to string, from numbers to strings, from integers. Is it from integers? or from natural numbers? Is this needed to put it in int? Maybe does Haskell have a natural number type? Not sure. Here's the Haskell function that implements this logic. Bang boom into string. Bang boom x's. If x is larger than 10, then bang. All right. If it's less than boom, then if less than 10, then boom. You just don't repeating. Yeah. If x is larger than 10, then bang, else boom. And this is a function. Yeah, I'm totally confused by this. And then the pipe. And then the x. Oh, because before we did like just x times 2. And now we're kind of, you see, this is, now we're instead of, yeah, this is why I'm confused. Maybe someone will be confused too. Like, this is a big conceptual jump from like, look at this. We just had an x here, like a placeholder of sorts. And the x is what? Is this. And now we have what? This is the x, and the x is what? Is this. X is a list of, okay, the x itself is a list of x's. And the other condition is odd x. Do we have an odd function? Bang boom into string specifies that bang boom is a function that takes a list of integers and returns a list of strings. Okay, list comprehension. If x is larger than 10, then bang, else boom. X is the list comprehension that processes the input list. X's. Generator. Okay, x's. It iterates over each element x in the input list x's. Iterates over each element x in the input list x's. Condition. Odd x filters the list to include only odd numbers. Transformation. If x is larger than 10, then bang, else boom. Applies the required transformation. So this is the function that transforms the ints to strings. So if x is greater than 10, is replaced with bang. X is less than or equal to 10 is replaced with boom. Main. Oh, he's doing with main. Let numbers 1 to 20 print bang, bang, boom. Now, oh, this is nice. Let numbers be what? 1 to 20. Oh, yeah, I guess he already put the, no, he didn't. Bang, booms, bang, boom, bangs. He put the list, he gave it a list. ChatGPT made already like a main and put made let numbers is 1 to 20 and then print bang, boom, numbers. He connected the functions. Yeah, this is interesting. Where are we at the mark? 1 hour. That's enough. This is interesting. I need to contemplate more on this. I need to meditate more on this. Boom bangs, X's, if X's. Yeah. I guess these are things that you can get stuck. Like I understand what's going on, right? But let's say let's say you rephrase it. Let's say you change this statement and you put something else. Would I know how to write it down? I don't know. I'll stop here and maybe I'll think a bit about it. Or I'll just move on. Boom bangs. All right, let's stop with boom bangs. It was great.